Hey, this is Jason Molesky. In this example, let's take a look at logarithm transformations and exponential models. Now, Gordon Moore, one of the founders of Intel Corporation, predicted back in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is what we call Moore's Law, and it's one way to measure the revolution in computing. Now, here are the data on the dates and number of transistors for Intel microprocessors. We can see in 1971 that the processor labeled 4004 had 2,250 transistors. In 1993, when the Pentium chip came out, we had 3.1 million transistors. And in 2010, when the 8-core Xeon Nehalem EX processor came out, we had 2.3 billion transistors. Now this figure shows the growth in the number of transistors on a computer chip from 1971 to 2010. Notice in the graph, we use the variable years since 1970 as the explanatory variable. That'll come in handy later on in part of the problem. Now, if Moore's law is correct, then an exponential model should describe the relationship between these variables. And in looking at the scatter plot, it does look like that might be the case. Now, the scatter plot here shows the natural logarithm, which is the log base e, or natural log, of the number of transistors on a computer chip versus the number of years since 1970. Now, based on this graph, we need to explain why it would be reasonable to use an exponential model to describe the relationship between the number of transistors and years since 1970. Well, if an exponential model describes the relationship between two variables x and y, then we'd expect a scatter plot of x versus the natural log of y to be roughly linear. And we can see here, if x is the years since 1970 and y is transistors, then x versus the natural log of y does have a fairly linear pattern, especially up through the year 2000 or so. So it does appear that an exponential model seems reasonable. Now, Minitab output from a linear regression analysis on that transformed data is shown here. Let's give the equation of the least squares regression line and be sure to define any variables we use. Now recall in Minitab output, when we want to write the equation of a least squares regression line, we look at the column labeled coefficient. That should give us the information we need. So in this case, our y variable was log of transistors. So we're actually predicting the log of transistors, and that's going to be important in the next step of the problem. So the predicted log of transistors is equal to the constant value, 7.0647, that comes from the coefficient column in the constant row, plus 0.36583 times our x variable, which was the year since 1970. Notice in the coefficient column, the 0.36583 is the coefficient for the x variable. Now, using that model, let's predict the number of transistors on an Intel computer chip in 2020. Now, we have to be careful here. We don't just plug in 2020 for our x variable. Recall, we defined it as years since 1970. So in this case, we'll actually have to plug in a 50 into that equation. And doing the mathematics, we find out that the predicted log of transistors is 25.3562. Now, we want to predict the number of transistors, not the predicted natural log of that. So to find the predicted number of transistors, we'll have to use the definition of logarithm as an exponent. If the natural log of the transistors is predicted to be 25.35, that means log base e of the transistors is predicted to be 25.3562. And if we take the definition of logarithm as an exponent, we can then say e to the 25.362 power will be the predicted number of transistors. In this case, that's 1.028 times 10 to the 11th power. Or in other words, the model predicts that an Intel chip made in 2020 will have about 100 billion transistors. Now, a residual plot for the linear regression model from part B is shown at the left. Describe what this graph tells us about the appropriateness of this model. Well, the residual plot here does show a distinct pattern. We see a little bit of scatter here, but then a definite drop down and back up. We kind of have this wavy pattern going through our residual plot. Remember, patterns aren't good in a residual plot. So they're going from positive to positive as we move from left to right. However, when we look at the values of the residual, they're fairly small in size to the relative to the size of the transformed y values. Also, when we looked at that scatter plot of the transformed data, it was very linear, much more linear than the original scatter plot. So when we couple the size of the residuals with the fact that that scatter plot for the transformed values was very linear, we can feel pretty reasonably comfortable using this model to make predictions about the number of transistors on a computer chip. Now, for some additional practice with logarithm transformations and exponential models, try exercise 41.